For our next session, we have none other than Anima. Anima, as most of you all probably already know, is a professor at CalTeck. We used to work together a long time ago. I think she's one of the most amazing women there is in the field of AI, and not just a woman, an amazing researcher. So, Anima, we're very glad to have you on. And we also have James, who is, at Abacus.AI. He leads both NLP as well as anomaly detection. So, James will be talking to Anima today.
Great, thanks for the intro, Bindu. So I think it's probably worth also noting that Anima is also the Director of Machine Learning Research at NVIDIA. So certainly an honor to have you here today. So we're going to be speaking about all things beyond supervised learning. So I thought, let's just set the stage. So Anima, what would you, can you give us a definition of supervised learning and maybe give like an example where that's just the best thing to use and it works great?
Great to be here, James, and great that Bindu is organizing this really awesome event, and and it was great to also hear Richard, talk about all the aspects from AI economist to search. So pleasure to be here. So indeed, diving right to the aspect of standard supervised learning is really about understanding the distribution of training examples and hope for some generalization, to test samples but from the same distribution. That's our standard loss function minimization. We are getting lots of examples from our distribution, and then if you now have new examples at test time, you hope to do well, So that's the framework, and it's really about learning mappings, between input and output. And so that's where you can have a huge diverse set of applications. The most common use cases are classification, but also could be segmentation, Could be, like understanding the scene. It could be, of course, aspects of understanding sentiment in the language. So all these applications where, you can go label data, and in most scenarios, it's human labeled, although we could think about automated labeling schemes. But it's really about learning mappings, So that's how I think of supervised learning versus everything else.
Yeah, no, I totally agree. It's sort of like, I think the core thing is you're learning a function. It might be a probabilistic function. It might, the outputs of your function might be entire graphs, but fundamentally there's a function in there. And as you pointed out, and sort of hinting to what we might talk about in the future, you're then assuming that that function can then be used in the future, which makes some assumptions about invariances of some sort between the training phase and the testing or production phase. Okay, so I think that sort of sets the stage of that's supervised learning, and that's what we're not going to be talking about. Okay. We may come back to it. Now, so let's start with one of the, maybe one of the alternatives that if you were just to search for this on Wikipedia, if you search for supervised learning, it's probably going to tell you about unsupervised learning. Now, which I think maybe 5-10 years ago, that sort of had a fairly well-defined definition. Of course, it always changes, but so when I think of something like unsupervised learning, I'm thinking of techniques like dimensionality reduction, like clustering, like topic analysis. So I was wondering if you could tell us about maybe one of those techniques, sort of the central difference to supervised learning in that example. And I think hopefully we can then talk about some of your older research about spectral methods in that area. So.
Yeah, certainly. At a high level, what distinguishes unsupervised learning is not just the absence of labels, You can say like, oh, I don't have labels, I just have my data samples. But it's also the goal that is different, because instead of trying to learn a specific function or a mapping, what we want to understand is the structure of the data itself. So at the, if you want to learn everything about the data, that would be the data distribution. So that would be a generative model, But you could also learn specific aspects of data, and that's where what you mentioned, dimensionality reduction, learns, if this full observed dimension is not where the data lives, but certain reduced dimension, right, representation is good enough to represent the data set, right? How do I get to that? But at a high level, it's really about understanding the structure in the data itself, right? So I like to use Richard Feynman's quote where he says, what you cannot create, you cannot understand, right? So ultimately, we need to be able to have generative models that can model the rich phenomena in the world, whether it's videos or language, and we're getting much better, right, at those. But still, there's a long way. It's much easier to do a very specific task and say classify cats and dogs versus generate all possible dogs in the world. I mean, we're getting there, but to do it with the diversity of all the data we have is quite a complex one. And that's where, right? I mean, ultimately, if we could do generative modeling, we've solved everything, right? Because if we know how to generate a dog with a specific kind of, say, pose and angle, then we can also classify it to say it's a dog. But the problem is generative modeling is much harder. So most of the time, we limit to certain targeted supervised learning tasks, and with the labels we can learn this mapping much more effectively. So there's kind of like the more long-term versus the short-term goals for machine learning.
Interesting that you picked a Feynman quote there, because I think it's an idea that keeps coming back. If you can't create something, if you can't generate something, that reminds me of Jeff Hinton when we were starting at the beginning of the deep learning revolution, when I think it was to classify digits, first learn to create them. Anyway, a little bit later, computers got faster, techniques got better, and then it's like, oh, well, maybe we don't need to generate them anymore to classify them. But here we are again, and there's lots of cool new generative models in that space. So the reason I started talking about some of these sort of maybe more now classical unsupervised techniques. So I guess the first time that I learned your name when I was getting my PhD was for your work on tensor decomposition methods and spectral algorithms for estimating models. So I'm wondering if there's anything you wanted to say about that, because I'm just curious. So I see that some of your work there has then resulted in your future work. You've just been very happy to use tensors in all of their flexibility and glory. I was just wondering, how's that line going these days?
Certainly, James. And to me, I think, the aspects of, right, looking into understanding the structure of data, right? So before the deep learning era, what we did was to posit probabilistic models, right, that are capturing at a high level certain latent variables, right? So that would be not directly observed, right? We don't have labels because this is unsupervised learning, but how do we go and estimate them? And the standard technique was to do expectation maximization. So effectively, you're doing a local search on the likelihood function, right? And this is a specific kind of local search. But ultimately, the challenge is the dimensionality of the problem. As it gets bigger, the search is very hard, right? This non-convex optimization tends to fail, and this is very slow. It's also hard to parallelize, all these challenges with having these models. And so I think to me, the outlook is these kinds of models are really important, say in healthcare, for instance, where uncertainty quantification is needed, right? So if we look at in a probabilistic lens, what are the latent variables? How do we interpret that? What is the uncertainty they have that can relate to, for instance, the gene admixture models, right? What is the ways different genes interact together? So that's where I think they, even today, have a really big role to play. But to me, I think the aspect that made this very interesting was algorithmically, how do we solve for learning these latent variables? And so a canonical model is this topic model, right, or called latent spatial allocation, which has indeed seen extensive works. And there, the goal is to learn these latent variables that are the topics, right? So you can think of the use case of all, like, say, news articles or journal articles, right? And each one could have multiple topics in them, right? So how do you learn what are the underlying topics without having labels? And so the aspect, what we showcased was the ability to do it without expectation maximization, but as a moment-based approach. So as you mentioned, looking at co-occurrence in data, right? So the natural co-occurrence is looking pairs of words. If you just looked at pairs of words that occur together in the document, that may give you some information about the topic. But what we show is matrix methods, right, like PCA, like doing principal component analysis, is inherently limited because it's linear. So that we're going to higher order moments, such as looking at co-occurrence of 3 words in documents. So all triplets, if you look at them, and that's a big tensor. And how do you look at the principal directions in that tensor, right? How do you decompose that tensor by expressing them as a combination of a small number of topics? So those operations let you tease out the topics automatically without requiring labels. And so the benefit of these methods is that you can run them at scale. I mentioned looking at all triplets, right? Of course, we are never going to write them into memory because this would be untenable, right?
Mm-hmm.
Instead, like algorithmically, how do we solve for these tensor methods effectively? I think that aspect is what was the nice insight. And since then, right, like these aspects of looking at tensors as extensions of matrices to more dimensions, looking into dependencies, right, like on higher order statistics, right, is also useful for, say, designing neural network architectures that can capture higher order dependencies. We've seen that they're being effective in compression, they're being effective in better generalization. So that's one angle of it, that these methods, right, are also applicable beyond. But also in the quantum realm, right, where tensor networks are the ways to, show, like, kind of model entanglement at different levels of strength. And these are naturally occurring systems. So for us to be able to simulate this and design algorithms on that, it's also a really interesting bridge. So, I guess at the core of it, what I like is tensors as an algebraic object are really versatile and useful in many machine learning applications. But our insights from latent variable modeling is also, right, applies to many other fields beyond what we had expected and started with.
Yeah, that's very cool. I mentioned it just because I mentioned some of the tensor work had like, well, that can now be used for supervised learning in some cool ways. Yeah, actually, I guess partially my own ignorance and hopefully for interest of the audience. So when you mentioned that, potentially, using tensor operations, say in deep learning, rather than just restricting yourself to lots and lots of matrix operations, do you have so you mentioned doing things in quantum mechanics, but do you have any other good examples where you really see sort of a big gain or something you couldn't do before by expanding your mind a bit?
Yeah, indeed. First, even just the topic modeling itself, right? We built now large scale, services that do this topic modeling at scale. When I was at Amazon Web Services, right, along where I met Bindu, right, we did this to run at the cloud scale. And and that's where, the idea is these methods are actually really lightweight and practical, right? I mean, you could do deep learning based methods to extract various insights, but if you have really large document corpus and long documents, right, this is kind of giving you high level topics, and this is much, much faster, right? Because looking at just the co-occurrence statistics is going to be much quicker than learning a heavy deep learning model and then actually, right, running that on a huge corpus. So I would say that this is a much more like kind of high level topic modeling versus a much more deeper understanding of the language and the text, which many of the language models do.
Got it. Okay, cool. Now, so at the beginning of this, you mentioned generative modeling. So one version of supervised learning is just generative modeling, and just given a sequence or some other sort of structure of data, and just the question is, can I generate that data, or can I sort of describe how likely that data is? So again, thinking back, some of the classical techniques there, starting from sort of some simple density estimation methods, and then when deep learning came along, people started coming up with ideas like, autoencoders for being able to generate images, which then potentially turned into GANs and other such things. So wondering if that's a sort of area that you're actively involved in at all, or have anything interesting to say about, GANs for generative modeling, and yeah, how's that going?
Yeah, certainly. NVIDIA, right? We've here the team at NVIDIA, we've been doing a lot of really cool work on GANs, right? Including very high resolution photorealistic generation. Like if you've looked at the GoGAN demo, for instance, right? Like you can turn into an artist painting landscapes by only kind of giving high level kind of guidance into where should the mountain be, where should water be, and so on. So I think all these show like the ability of GANs to scale up to really large scale settings, right? And one aspect we've been focusing in is on controllable generation. So how do we go from like unconditional GANs, which is cool, right, to highly controlled attribute specification, and that's what we would need in lots of applications, right? For instance, we are saying we can use GANs to generate synthetic data for supervised learning. But for that, you need to be able to generate specific kinds of data, right? For instance, in order to remove bias, we may want to generate data of certain attributes and categories that's not well represented in human labeled data. But that requires us to then, not just reproduce the training distribution, right, in terms of generating samples, but have control on the attributes and compose them in specific manner, which is a much harder thing to do. And so one aspect we've been looking into is this combination of like, first of all, right, supervised or semi-supervised, right? So you could have labels of attributes and you try to train a conditional GAN model, but there could be lots of unlabeled samples, right, of where these attributes are not labeled. So how do you combine the different loss functions and show that, in that work, what we showed last year was even if just like 0.5% of the data is labeled with attributes, you can be very effective in disentangling, right, these different features, and then be able to control very effectively on what you want to generate.
Very cool. It's 0.5%. That's really quite a strong result. Yeah. I think it's sometimes you see semi-supervised papers, and you get a little bit upset when I see we only use 20% or 30% of the data, and it's just like, okay, it's an efficiency, but it's not. We haven't hit an order of magnitude there. So 0.5% is very cool.
And in this, because this is different, right? This is different from like classification or other tasks where the focus is on getting very high accuracy on that specific task. Whereas here we're saying, you need to learn the overall data distribution anyway, right? And to do that, you need to disentangle the various attributes. So the model, when it's trying to generate say, a sample, it has to learn, like in a face, where are the eyes, where are, which angle is it? So it has to implicitly learn that anyway. But, explicitly, if you say these are the attributes, this is, the view is like in this angle, or there are glasses, or a few of those, it's already able to kind of pick related to the latent features it's already learning. And so that's why, this is a different regime than what we see in semi-supervised learning for a specific task.
Okay, good point. So it's certainly an interesting idea, like being able to go from generative models to controllable generative models. And as you said, potentially you could use those then for supervised learning. You're now potentially generating the data, in regime, like areas where you don't have so much data, potentially balancing your data in some sense. Does one have to be concerned about these models just inventing things that really aren't there, and then your supervised models learn it as if it's truth? And is that something that we can think about and control against, or what are your thoughts on that?
Yeah, and that's always a hard question, right? Because ultimately there has to be human in the loop, right? If you just kind of say, oh, generate, right, everything from this model and just kind of blindly feed that, right? It's, I think, not going to be in many cases, the right solution, right? So, I mean, at least there has to be some kind of curation to see, first of all, is this model trained well? Is it generating something meaningful? But of course, it becomes much more difficult, let's say, in scientific domains where there isn't a ground truth, right? Like, how do you then generate, you think these are the disentangled features, and now you're combining them in entirely new ways. So there has to be some kind of ultimately physical validation, right? Some experimentation. So everything here is, to me, is useful if you're trying to kind of simulate or kind of trying to search over a big space, do that much more effectively as latent space of these generative models. But ultimately, there has to be some other validation whether this has been a meaningful generative model.
Okay, that makes sense to me. Now, I think, as I said, we have to come back to supervised learning at some point, and that we've already done so. So I think, in many ways, we've described the long version of what might now be called self-supervised learning, which I think was a great term to coin. It sort of really helps you think about it. But I should imagine, I guess it's so an area that people might know about this best is in language modeling. So things starting with Sesame Street acronyms and everything since of just got a lot of text. Can I predict the next word or something else like that? Building great language models. But I'm wondering, do you have any specific experiences in the self-supervised learning world with access to so much data?
Yeah. I mean, to me, like the self-supervised learning, right? I mean, it's the whole idea is how do you kind of generate labels based on already known invariances in the domain. So if you have images, you crop part of the image, you should still be able to recognize what's right in the whole image. Or you kind of add noise, you still should be able to recognize. You rotate it, you should be able to do, right? So it's really about, like right now we don't have an efficient way to convey to the model that these are the invariances, your answer should not change. So the easy way is to augment data and say, kind of like this is the label, right? Even after these changes. And so, but to me, in the ideal world, you should be somehow able to bake in directly into the inductive biases in the model, right? For instance, we have the class of equivariant neural networks, right? For instance, to model molecules, there's 3D symmetries. You rotate the molecule, the dipole moment should also correspondingly rotate, right? So you have to force the network to be changing with the rotation, the answer in terms of like what is the dipole moment predicted for this molecule. And so there we, in those cases, we've designed networks that directly have this in equivariance or invariance. So then we don't have to worry about data augmentation. But in a domain like, say, natural images, this is very hard to provide, right? Because it's not easily structured into a neural network. Because for instance, this rotation, from the 2D, first of all, you have to infer the rotation, right? And then you have to make the neural network be equivariant to that. And trying to do that explicitly is really hard. So instead, implicitly, can we have the network learn these invariances through creating these data augmentation? And there we've seen lots of really great success stories, in many cases, even beating supervised baselines, right? So like, especially like having this in the computer vision domain, like you can do self-supervised learning with lots of data augmentation, even beat many cases the classification performance of supervised learning. And so what we see in these cases, for instance, the ICCV paper we had a few months ago was showing the ability to take weak supervision and add self-supervision on top of it to do tasks that otherwise would be very labor-intensive to label. For instance, doing instance segmentation, right? So, in very complex scenes, you have to go to every instance, right? If there are lots of people dancing, that was one of our demo videos. If to go and have a human label the instance segmentation masks of each one, right? And then you want to Also if you want to get correspondences, right, you have to go, have the human like kind of say which part here corresponds to which part in the same image or a different image. So instead, what we said was it's much cheaper to have bounding box supervision. This is perhaps the most standard localization task, right? You can have humans very quickly just put a box around different objects. So using only the bounding box and combining with self-supervision, what we are able to show is the ability to get very precise instant segmentation masks, semantic correspondences, everything for free, right? So you don't need detailed labels, but you can get to much more nuanced tasks using self-supervision on top of weak supervision.
Very cool. Now, you're mentioning of sort of learning invariances, that sort of thing. Well, I'm not sure if this fits the brief, but when I was looking up some of your latest research, one of the things that caught my eye was your work involved in trying to put prior knowledge into neural network-based systems, which I think I saw something that caught my eye was learning to fly a drone, but making sure that you still learn a stable controller. Am I right to think that there's a link there between learning invariances, equivariances, and here putting prior knowledge in? I wanted to shoehorn that work in because it seemed rather fun. But
yeah, thank you. No, indeed there is, right? Because any machine learning model is a combination of data and priors, right?
Mm-hmm.
So the more priors you have, the less data you would potentially need if those priors are the right priors. Of course, the difficulty is if you put the wrong priors and you make the model inflexible, then you cannot fit to the distribution, right? And that's the delicate balance on what are the appropriate priors and can we impose them in a way so that the optimization landscape is not too difficult for training, right? And then through that, can we reduce our dependence on labeled data? And indeed, we see those in those examples, right? You can train with much fewer samples when you incorporate these constraints. And also the aspect of, right, I mean, in those situations like safety and stability, that would be out of distribution, right? So you cannot just rely on data. You have to incorporate these constraints to make it successful in that domain.
Oh, so I think in which case it's probably time to talk about out of distribution. So going right back, we talked about supervised learning. You're learning a function, and then you learn your function, so you're going to apply your function. But if you now apply that function to an input that wasn't in the domain of your training data, well, in some systems, who knows what it's going to do, and other systems you need that sort of prior information. So I'm wondering if you could maybe speak more about that situation where, how does supervised learning break down in this case, and what is the toolkit for dealing with that?
Yeah, indeed, this has huge real world implications, right? Because almost every domain you can think of, including, right, what I'm sure you're working on, there's a huge changes, right, from where the model is trained and where it would be applied on it. And you can't possibly incorporate all that because the world has a long tail and you cannot capture all of that in the training distribution. And so to me, I think the very first flaw with standard loss minimization in supervised learning is, the system just doesn't know what to do beyond this, right? It acts as if it's the training distribution itself. And that's where things go very wrong. To give you an example, right? It's better with pictures, but I'll just ask you to imagine. So think of your, training distribution in this toy case to be all red apples and yellow bananas, right? So that's all you've seen during training. But let's say now at test time, I show you an apple that's yellow, right? Then you would think it's banana because you've never seen a yellow apple before, right? So this is a very kind of toyish example, but shows the aspect that if you now see features combined in an entirely new way, you don't know what to do with it because you have not trained on those scenarios. But there's another nuance here, right? So it's not just that it's wrong. It can be overconfident because it's only seen these yellow bananas. It thinks this has to be a banana with high confidence. So there's very likely that you may end up with a system that's not just wrong, it's overconfident when it's wrong. And in fact, the real world implications of this, if you've seen some of the gender shade studies and the talks that go with it, you see like these, right, like Black celebrities being misgendered, but with high confidence, right? And at that time, what was publicly available, face recognition systems. So I think what this is kind of showing is that we, have to start with dealing with distributional shifts in terms of uncertainty calibration. Right? So we can't expect this trained model to be universally correct, right? That's an impossible ask. But to begin with, can it at least fail gracefully? Can it be humble? Can it give us the right confidence calibrations? And that's where one line of work that one of my postdocs, Angie Du, who's now a professor at Johns Hopkins, right? She looks at it from the lens of adversarial risk minimization. So in the standard loss minimization, you're kind of thinking your data is perfect, right? There's no label noise. I want to perfectly learn this function. If I had infinite samples, I would completely fit to, right, the labels that are present in my data. But in adversarial risk minimization, we are saying, we should expect changes in distribution between training and test. And so can we incorporate this? And can we learn a loss, based on a loss function that accounts an adversary that shifts the distribution? And so what this practically ends up being is to also have a test time detector that can detect which samples are much more out of distribution from training data or not. So you're not just classifying your sample, you're also judging, is this sample very different from my training data or not, in an implicit manner? And in fact, this is also so natural for us, right? I mean, if we encounter something very new, even though we may be able to know what it is, a part of our brain is like, this is new, right? So we need to kind of bring that element of surprise into our neural networks to also have it judge, am I doing inference on samples that were similar to what I saw in my training, or is this different? And based on that, can we automatically change our confidence levels?
Mm-hmm. That's something very interesting. I mean, I'm currently working on anomaly detection, and during my PhD, I got kind of interested in model checking, or the term I preferred was model criticism. So, model checking sounds like you're assuming that your model is correct. Model criticism maybe reverses a bias, and that was all about understanding, where does this model not know what it's doing? Where is it?
Precisely.
Correct. Super important stuff. I think you used a good term there, failing gracefully. So I think in the examples we're talking about there, we're talking about, some failure modes are, in classification, you're getting overconfident, possibly about the wrong classification. And that's sort of, it's a failure, but it's also not a graceful failure. And so, that has big issues, but, take this to another situation. So autonomous vehicles, perhaps, or, so could be any vehicle for that matter. Could be a car, could be a drone, or that sort of thing. I think there, the idea of failing gracefully, again, is maybe important. So was I correct in understanding some of the work I saw that, at least for learning controllers of drones there, or maybe you can tell us there, what is the equivalent of failing gracefully when you come to controlling, a vehicle or an aircraft?
Yeah. I mean, indeed, there are so many facets there, right? So one is looking into what are the safety requirements. If the safety is at this height above the ground, the velocity cannot be beyond a certain value, right? So how do you kind of always ensure that even when there is turbulence and all these forces? Right. So, and so the one aspect could be, you could do extreme things like spectral regularization, right? So meaning you regularize the spectrum of every layer of the neural network. So it has a bounded Lipschitz norm. So, and that by definition guarantees stability. And that's what we did in the case of the drone, because it's still fairly low dimensional system, right? But this wouldn't scale all the way up to higher dimensions. And so what we then asked was, can we, of course, if we try to land the drone very fast and safely all together in the very beginning, this is hard. right? But like a curriculum learning, I mean, even humans, right? Like if we're trying to drive, we drive slowly and then pick up speed. Or if we are trying to land a drone ourselves, we are careful in the beginning. So this notion of safe exploration, right? So first, the drone decides to land slowly based on the safety, right? Again, this is the uncertainty quantification. So if you have the right uncertainty, beyond the speed, right, your probability is like not good in terms of meeting the safety requirement. So you first do it, you collect data because we need data to understand the turbulence this system is facing. And then over time, we speed up gradually, right? And then we can handle even much higher speeds while maintaining the safety requirement. I think these kind of, right, like self-learning systems that have like kind of generate their curriculum based on where they see are new aspects to pick up, but it's still safe, right? Or it's still meeting the requirements of your system. I think that's very important because we can't possibly give all careful supervision of every aspect, right? It has to at some point learn on its own.
Indeed, it was no, it just caught my eye as it's a very cool area where to point out that you can improve efficiency over some classical controllers by putting a neural net in the loop, but you want to make sure that here it's not even failing gracefully, it's not failing. It's staying within, making sure that everything is still, you can still prove stability.
So system is dead if it fails, right? So in this case, the drone crashes, that's the end of the story. So, and that's what we call the safety critical systems.
Exactly. So it's cool work that's showing that indeed you can get some improvements over some classical control theory, but in a safe way.
Exactly.
Okay, let me see if we've got any questions. So I was just reiterating that because we didn't get a question. We got an assertion from Alexander V that classical control theory is enough for drones, and I encourage you to look into the research we've been talking about. You can improve, and you can improve in a safe way. Let me see. Okay, let's see this question. Oh, I think they may have got another statement. So we've got Anima and panel. I agree there are so many clear assumption failures in ML right now, namely Gaussians, linearity, and spectral analysis is looking in the right direction, and that's what I'm looking into also, says Mark Cox. So don't know if that generates any comments in your mind, Anima, or?
Yeah, I think there is a lot of ways to kind of use spectral analysis, right? Especially if you're dealing with large scale data, and these are, you can think of them as pre-processing mechanisms, right? To get the dimensionality reduction, get high level insights, and then you could do deeper analysis with deep learning based models. So that's one way to think about these methods, right? The other is also looking at hybrid models, right? That could use some neural components, but also have probabilistic modeling. If you want to kind of have interpretable hidden variables and use these techniques because they're really cheap and fast to do it at a large scale.
Okay, and then also going through the comments, I think we got to, okay, so let's see if this, with GMS, what were they asking? Oh, yes, they were wondering if the idea, if there's if adversarial models might be present in our own minds to some extent. So he mentions the bicameral mind models. So we don't just talk to ourselves, but we argue to ourselves to solve problems. I don't know if that's anything you've thought about. Have you thought about the AI or neuroscience side of things when it comes to adversarial thinking?
Yeah, I mean, absolutely. I don't know if it's necessarily adversarial, but there is the aspect of what, having some form of generative model in our mind, right? There's an internal model of the world. That's what gets us to dream. That's what gets us to hallucinate. And that's what gets us to fill in the gaps, right? In all kinds of low light conditions or all kinds of occlusions, we are able to have that objectness, that whole understanding of the scene or the environment around us. And so one important mechanism is the feedback, right? So it's not just a feed-forward mechanism of signals going from our retina into the layers of the visual cortex, but we also have feedback from all other parts of the brain, like IT cortex, right? And so that's the internal model always filling in the gaps from the external inputs. And that's something we have been now working with, is how to bring in this kind of generative modeling, even if you want to do classification or other supervised learning tasks, all right? Because that aspect will now give like zero-shot robustness beyond just, right, the training distribution. Will also help with few-shot learning. That's one of the recent works we showed. So this notion of a feedback, I think, is very fundamental, right? And that kind of brings in generative objectives, even if our task is just some learning, some, say, mapping in a supervised learning task.
That's certainly an interesting idea. I remember, I'm not sure how much experimental data we have on this, but I remember Josh Tellenbaum once telling me that he thought maybe in some situations our brains are just, they're running some sort of sampler, generative sampler, but they just generate one sample and they go with that and see how it goes. But it was at least an interesting theory of what might be going on in the mind in some situations. Okay, now I think with that, we have 1 minute until the next session, so in which case I think I'll hand it back. So again, thanks very much, Anima, for excellent discussion. It's fascinating talking with you.
Thanks a lot, James. I really enjoyed it.